We have 9 so far. Okay. Okay. So it should work. Please. There it is. Okay. Good. Yeah, for some reason, sometimes it does funny stuff with us, man. Anyway, I'm glad we got everybody. All right, so people on Zoom, can you hear me out there?
Yes.
Yes? Okay, good. Okay. Let me see. All right, so let's begin class. So what I'd like to do is review a little bit. So we were talking about complex eigenvalues. So let's talk about complex eigenvalues and eigenvectors. All right, so I just want to review this example. I'm not going to put down all the details, but let me just at least put down the matrix for you and then recall what the eigenvalues were. So we had this example, and this was from last time. Okay. So we had A was a 2 by 2 matrix, 1, 1, -2, and 3. Okay. And in the last lecture, what we did was we computed the eigenvalues for this matrix. So let me just recall that. So if I take determinant of A minus lambda I, this was precisely lambda squared minus 4 lambda plus 5. And then we used the quadratic formula to compute what lambda was. So remember, we need to find the zeros. So lambda was 2 plus I and 2 minus I. Okay? All right. Now, for 2 plus I, here's an eigenvector. So if I take 2 plus I, then an eigenvector was, let's see, I guess it's -1 plus I and 1. Okay, and any multiple of that is an eigenvector too. Okay, and if I take lambda is equal to 2 minus I, then the eigenspace is spanned by the vector -1 minus I. Oh, and then I have a 1 here. Okay. All right, so we computed this out. So we figured out what the null space of lambda minus A minus lambda I was. And that's how we computed out the eigenvectors. All right, so then what we did was we looked at certain types of matrices which have complex eigenvalues. So here's another example that we looked at. So this was slightly more general. So A was a matrix where it's what we call skew symmetric. So it's A minus B, BA, right? Now, what we did was we saw that A can be written as R0, 0R, where R is the square root of A squared plus B squared, times A over R minus B over R, B over R, A over R. And another way to write this was, we can write it in terms of polar coordinates. So A over R is going to be equal to, let me just write it out. So A is going to be equal to R cosine theta, and B is going to be equal to R sine theta. Okay, so these are polar coordinates, as you've seen before. Okay. All right, so that means A over R is cosine and B over R is sine. So that means we can re-express this as cosine theta minus sine theta, and then cosine theta. Okay? So we can write A as a product of a matrix which scales. So this matrix scales. Okay? And this one rotates. So this is a rotation matrix. So the last matrix rotates a point theta degrees and keeps the length the same from the origin. Okay. All right, any questions on this so far? And then the point is that the eigenvalues of A are A plus or minus BI. Okay, so the nice thing about this matrix is the eigenvalues are just given in terms of the coefficients of the matrix. It usually never happens that way. But for this matrix, it is quite nice. All right, so now what I want to do is I want to actually compare these two examples. So to compare these two examples, I'm going to rename things. That's the advantage with this iPad. All right, so instead of calling the second example A, I'm going to call that matrix C. Okay, so let's call this C, call this C, and call that C2. All right. Now, it turns out that A is going to be similar to C. Okay. So let me put that as a bullet point. It turns out that A is similar to C. Okay. And so what I'm going to do next is I'm going to describe how A is actually similar to C. Right? And this is via this theorem. So here's the theorem. Okay, so let A be a 2 by 2 matrix with eigenvalue let's see, I guess well, okay, we'll just say it this way, A minus BI. Okay, so once we have the A minus BI, I'll specify what the A is. Okay, and eigenvector V, which could have like complex entries. So then A is similar to C. Okay, so A, P, C, P inverse. Now P is not going to consist of eigenvectors because C is not a diagonal matrix. Okay, so where C is a rotational matrix with scaling, so it's something which appeared in example 2, and the way you can find out P is you take the real value, the real part of the vector V and then you take the imaginary part of the vector v2. Okay, so I'll show you how to do that in this example. Okay, any questions on this? All right, so let's apply this to the example. So apply this to the examples. Okay, so remember in the first example, we have 1, -2, 1, 3. And the eigenvector is a minus bi. Let's just take this one, 2 minus I. Okay? And the eigenvector is, so here v, okay, so I got to go back up here. It's -1 minus I and 1. Okay? So this is an I over here. Okay, so what does the theorem say? Well, this has an eigenvalue, 2 minus I, all right? This is a real valued matrix, and we have the eigenvector, an eigenvector for this eigenvalue. So now I can write the C out. So what is A in this case? Anyone?
2.
2, good. What is B?
1.
1, good. All right, so now we can write the C out. So C is going to be equal to A, which is 2, minus B, which is -1, B, which is 1, and A, which is 2. Okay, good. And then what I need to do is I need to take the vector V. Now let's write it out in terms of the real part. So that's -1, 1, plus the imaginary part. So I can pull the imaginary part out. That's -1. And what is the coefficient down here?
0.
0. Okay, so you write your eigenvector in terms of the real part plus the imaginary part. So this part, I can put it in like red here. So this part is the real part of V, and this part here is the imaginary part of V, not including the I. Okay? All right, so now we can write our matrix P out. So P you get by putting the real part down the column and the imaginary part down the other column. Okay, so what matrix do we get?
-1, -1, 1, 0.
Good. 1 and a 0. Okay, good. All right, any questions on this? So this actually gives you a nice little recipe. As soon as you have a complex eigenvalue for a 2 by 2 matrix, then you know that it's going to be similar to one of these A minus BBA matrices, which involves a scaling and a rotation. Okay, it's not diagonalizable, but it's similar to this type of matrix. Okay, good. All right, so that finishes the section off on complex eigenvalues. What I'd like to do next is sort of show you some applications of eigenvalues to discrete dynamical systems. Okay, so applications of eigenvalues, and let's say eigenvectors to discrete dynamical, let's say systems. Okay. All right, so that's what we're going to look at next. All right, now there'll be various applications that I'm going to show you. So the application that I'll probably spend the rest of this class on is an application involving the Fibonacci series and Fibonacci numbers. So we'll actually look at this closely, and then on Monday we'll look at economic models and then predator-prey models. Okay. All right, so this is kind of one of my favorite applications. So I have to talk about the golden rectangle first. All right, so what is the golden rectangle? Well, it's a rectangle which looks like this. So there are two parts. It's a rectangle which is sort of divided in a certain proportion. So this is A, this is B, this is A, and of course, this whole length is A plus B here, okay? Now, it's a golden rectangle if the proportions sort of match in a certain way. So namely, the proportion of the side here, A plus B over A, so sort of the length over the width is proportional to just A over B, which I'm going to call phi. Okay, so this actually defines a golden rectangle. And there are many, many, sizes of golden rectangles, and this is sometimes used. You can look it up in Wikipedia. It's used in architecture and comes up in other applications. Okay, so the question is, one question is, what is A over B? I mean, is it a certain number? So let's ask ourselves that question. What is phi? All right. Now, what we can do is we can just sort of write phi out using this equation. So we know that 1 plus b over a is equal to phi. Okay. And of course, b over a is just 1 over phi. Okay. And, now you can just multiply phi on both sides, right? So phi plus 1 is equal to phi squared. So we get that phi squared minus phi minus 1 is equal to 0. Okay, now you use the quadratic formula. And I don't know if I should do it, I'll just do it. Phi is equal to minus b, that's 1, plus or minus b squared, that's 1, minus 4, a is 1, c is minus 1 over 2. So the answer is 1 plus or minus the square root of 5 over 2. Okay, so this interesting number comes up as the ratio of A and B. And this is actually called the golden ratio. Okay? And I'll tell you, I'll sort of say what these numbers are. So 1 plus 5 over 2, that's approximately equal to 1.61803. And 1 minus square root of 5 over 2 is approximately equal to minus 0.6180. Okay, one is negative, one is positive. And this one's often called the golden ratio. Okay, any questions up until this point? All right, good. All right, so now I want to sort of consider the famous Fibonacci series. Oops, only one end. Okay. All right, so let's start with the Fibonacci series. So you take 0 and 1. So how do I get the next number?
You add the previous two.
Okay, so what do I get?
1,
And the next one is?
2,
Okay, next one?
3,
Okay. Keep going?
5,
Okay,
8,
okay,
13,
okay,
21.
21. All right. Okay, so that's how the Fibonacci series goes. So we can recursively define this. So the k plus second Fibonacci number is obtained by the k plus first one plus the kth one. And we know that f of 0 is 0 and the f of 1 is going to be 1. Okay, so at the 0 stage we get 0 and at the first stage we get 1. And then this gives the recursive relation in order to get the, you just keep recursively using this formula in order to get the Fibonacci sequence. All right. So now I ask you a question. What is the 1,000th Fibonacci number? Okay, any guesses or any sort of ideas about how to compute this? Oh, we could run it on a computer. I'm sure I'll crank it out in like, within 5 minutes at least, maybe in 30 seconds. Maybe we can just go online and do it now.
Yeah.
All right. So what we're going to do is we're actually going to find a formula for the 1,000th Fibonacci number. And what we're going to do is we'll actually find a formula by analyzing what's called a difference equation. Okay, so let me sort of set up a system of equations. So we want to set up a system of equations. Okay, so the first thing we're going to do is at the kth, we're going to make UK to be the k plus first Fibonacci number and the kth Fibonacci number. Okay. All right. Now we know that UK plus 1 is equal to FK plus 2, FK plus 1. Okay, you just replace K by K plus 1. And so we have these two equations. We have that FK plus 2 is FK plus 1 plus FK. And then we sort of have a dummy equation, namely like Fk is equal to K plus 1 is equal to Fk plus 1. Okay. Now we can get from UK plus 1 from UK by just doing the following. I could just take this matrix here and multiply it times UK. Okay, so you can see that the first entry of UK plus 1 is going to be Fk plus 1 plus Fk. That's just matrix multiplying this one with that one. Okay, and then the second equation is just given by Fk plus 1 equals Fk plus 1. Okay, so we've encoded these two equations using this relationship here involving matrix multiplication. All right. So now let's make a following observation. So we have that U1 is equal to A times, and let's call this matrix A here. Okay, so U0 is equal to U times A1. All right, so what about U2? That's A times U1, which is A times U0, which is a squared times u0. Okay? So u3, you just follow the same procedure. That's a cubed times u0. Okay, so I should say what u0 is. So u0 from the very start is just the vector 1, 0. Right? It's the 0, it's the first Fibonacci number and then the 0th Fibonacci number by definition. Okay. All right, so so you just go along and uk is equal to a to the k u0. So if I knew how to figure out what a to the k was, right, I could just multiply times u0 and I would get the kth Fibonacci number. Right? Okay, so now I ask you, well, I mean, can you compute out a to the k? What tools do we have to compute out a to the k?
We can find a similar diagonal matrix.
That's right. So we can actually try to diagonalize a, and then it's not so hard to compute out what a to the k is. Very good. Okay, so let's assume that a can be diagonalized. Okay. So suppose a can be diagonalized, or it's diagonalizable. So a is going to be equal to s d s inverse. Okay. Now d will consist of eigenvectors. Okay. And so what do we get? We get uk is equal to sds to the k u0, which is the same as s d to the k s inverse u0. Okay? So S is going to consist of eigenvectors, as we know. Call them x1 up to xn. So this is the columns are eigenvectors. Okay? And now set S inverse u0 to be just the column vector c1 up to cn. Okay, so you have to know what S inverse is, and you have to compute out the value with S0, and you just get some column vector c1 up to c0. Okay. All right, so then if I multiply everything out, star becomes the following. If I take u sub k, this is going to be equal to c1 lambda 1 to the k times x1 plus c2 lambda 2 to the k times x2 plus cn lambda n to the k times xn. Okay, so if we know what the c's are, we know what the eigenvalues are, and we know what the eigenvectors are, then that's great. We have our answer. All right. So what I'm going to do now is I'm just going to apply it to this 2 by 2 matrix. We'll compute out the eigenvectors and the eigenvalues and see what we get. Okay, so let's go back to the problem. And let's recall what the matrix A was. I think it's 1, 1, 1, 0. All right, so just a 2 by 2 matrix. So let's actually compute out what the eigenvalues are. Okay, so we have P of A of lambda. That's a determinant of A minus lambda I, which is equal to 1 minus lambda minus lambda 1, 1. Okay, so we're just taking the determinant of this 2 by 2 matrix. And what do we get? We get minus lambda plus lambda squared minus 1. So this is lambda squared minus lambda minus 1. And we want to set that equal to 0. Okay, so what are the eigenvalues? Anyone?
1, -1.
Really? Have you seen this equation before? You've never seen this equation before. Like, how about right here? Yeah, okay. So we've already figured out what the eigenvalues are. They're the golden ratio and then its conjugate, okay? It's pretty amazing. I mean, so here's where the golden ratio comes up. So the eigen values are lambda is equal to 1 plus the square root of 5 over 2 and 1 minus the square root of 5 over 2. Okay, so let's label these lambda 1 and lambda 2. Okay, so from this equation, which is called a difference equation, so let me go back up here. So this is actually called a difference equation here. Where'd it go? Right here. So this is called a difference equation. So it's kind of like a differential equation, except, you know, we have to just iterate a process and it has an initial value condition, namely this part over here. So this is an initial value condition. Okay, so you take this difference equation with this matrix A. We found its eigenvalues, namely they turn out to be related to the golden ratio. All right, so to get what UK is, we also need to know the eigenvectors. Okay, so let's compute the eigenvectors. So for lambda equals lambda 1, what are we looking at? We're looking at 1 minus lambda 1, 1, 1 minus lambda 1. And these are distinct eigenvectors, eigenvalues. So what can we say about, is A diagonalizable or not? Yes or no? Well, I mean, the eigenspaces, you have one is going to have dimension 1, right? The other one's going to have dimension 1 also. The sum is 2, right? Which is equal to the dimension of R2. So the answer is yes, it is diagonalizable. Does everyone understand what I just said? When you just compute the dimension of the eigenspaces, you know that it has to be at least 1, right? It can't be any more than 1 because we have 2 eigenvalues. So, okay, so what's the, so all I have to do is I just have to figure out what a non-zero eigenvector is. And it turns out that if you multiply this out, this is 0. And then for lambda equals lambda 2, you can use Gaussian elimination to find another eigenvector. And it's, you know, looks the same basically, except I just replace lambda 1 by lambda 2. Okay, so if you multiply this out, then you'll get the characteristic polynomial. And then we know it's actually equal to 0 because lambda 1 and lambda 2 are roots. Okay. All right, so we know what S is. So S we obtained by just putting the eigenvectors down the columns. So these are the eigenvectors. Okay. Now, we need to compute out S inverse. So what do we do to compute out S inverse?
Flip the signs of A and D and swap B and C.
Good. So first of all, we switch A and D. And then we negate these entries, right? Do we have to do anything else?
Divide by the determinant.
Right. And the determinant here is lambda 1 minus lambda 2. Okay. So 2 by 2 matrix, it's fairly easy to compute out the inverse. And now what we do is we just multiply S inverse times U0. And that's just 1 minus 2 minus 1 lambda 1. U0 is just 1, 0, right? So that's not so bad. So what do we get here? We get, oops, I'm missing a 1 over lambda 1 minus lambda 2. Okay, so I get 1 over lambda 1 minus lambda 2, and I get a negative 1, right? And of course, this is going to be our C1 and C2. Okay, so far? And now we just put it all together. Okay. So now use the formula. Okay. So UK, which is FK plus 1 over FK. This is UK. That's equal to C1, 1 over lambda 1 minus lambda 2 times the eigenvector lambda 1, 1, and then you raise the eigenvector or value to the kth power. Okay, so I'm just using this formula up here. Okay, so let me just box this as a very important formula. Okay, so I'm using this formula for this example. So I have two terms. I have involving x1 and x2 and lambda 1 and lambda 2. Okay. All right, coming back down here, same sort of deal for this next one. So I get minus 1 over lambda 1 minus lambda 2. And then I have lambda 2, 1, lambda 2 to the k. All right. So I get equations for fk plus 1 and fk, and we're just interested in the kth Fibonacci number. So now we look at fk. So what is fk equal to? Okay, so let me just move that up. So we're looking at the bottom line, okay? So fk is going to be equal to 1 over lambda 1 minus lambda 2 times lambda 1 to the k. So I'm just looking at the coefficients down at the bottom, right? Minus lambda 2 to the k. All right. Now, when you write out lambda 1 minus lambda 2, what do we get? We get 1 plus the square root of 5 over 2 minus 1 minus the square root of 5 over 2. Okay, so the 1/2s cancel themselves out, and I get square root of 5 over 2 plus square root of 5 over 2. So I just get the square root of 5. All right, so now I'm there. So the kth Fibonacci number is 1 over the square root of 5. And then I put in the so remember this one is lambda 1 and this one's lambda 2. So I get 1 plus the square root of 5 over 2. I raise this to the kth power minus 1 minus the square root of 5 over 2. I raise that to the kth power, and I take their difference, and I divide by the square root of 5, and I get a closed formula for the Fibonacci number. Okay, so I don't know, how many people have seen like The Man Who Knew Infinity, the movie about Ramanujan? No one seen
Oh
that?
yeah, I saw that.
Yeah, okay. So, we start in the world of just integers, right? And it turns out that just, looking at problems with integers, like finding the kth Fibonacci number, you just can't stay in the world of integers. You actually have to go to the world of real numbers to actually find a closed formula. So this is kind of this idea in mathematics, is that sometimes there are structures sort of beyond like just integers that you actually need to solve problems which actually involve integers. Okay, so this is a case where this happens. So let me just remark, this is a closed formula using actual real numbers. Not just integers. Okay. And what's sort of amazing about it is if I pick any single k, this thing has to be an integer, even though you have like, irrational numbers in here. Right? And I find it quite amazing that, if you pick k equals, 2 million, this will still get spit out an integer. Okay. All right. Now we can make this slightly simpler too. So if you note that 1 over the square root of 5 over 2 is less than 1/2. I think I showed that. So actually fk equals the nearest integer to, well, I messed up here, to 1 over the square root of 5 times 1 plus square root of 5 over 2 to the k. Okay. So it's really enough to just compute this out. You could do it on your calculator if you want, and then sort of figure out, what the kth Fibonacci number is using this. All right. Any questions on this process? I know it was kind of involved, but this is going to be a process that we're going to use like in the predator-prey model too. So, questions? No? Okay, questions from the Zoom audience? Yes, no? All right, so let me just say what's going to happen next time. So as I mentioned, we're going to look at, I guess, what are called Markov processes. And then we're going to look at the predator-prey. Okay, great. Okay, so let's we'll stop here, and I wish everybody a safe and happy weekend. Okay.
Actually, I have a quick question.
Sure, no problem, Dan.
This to me seems like a more complicated way of using generating functions to solve for it. So would that be allowed on a test?
Maybe. I guess I mean, the thing is, I don't know if I would have you do something as involved on the test.
Okay,
They have you just apply the formula, for example. So,
all right.
Okay. Okay, any other questions? You're the only one left. Okay.
See you.
All right, we'll see you. Bye-bye. Okay,